So first I'm going to show the files that I modified within the kernel. The first file I changed was under the directory arch x86 entry syscalls. And then I'm going to nano to syscall 64.tbl. So I located three entries where the common ABI is used, and I used the three numbers, 335 to 337, as my unique system call numbers. I have three system calls here named get proc log level, set proc log level, and proc log message. Now this was an important step because the kernel relies on this table in order to map system call numbers to their corresponding handler functions. Then edited the syscalls.h file under this directory here. Syscalls. H was here that I declared the three system call function prototypes using the ASM linkage macro. I defined the parameters that are used within each system call definition and will return a value of type long. For the log messages parameter, I made sure to include a pointer to memory and user space where the log message is stored. The last file I edited is sys.c where I implement the system call functions. At the top of this file here, I added three new include statements which I used within my implementations. As for my definitions, at the top here is for the system-wide process log level. I simply used a global kernel variable of type integer, which was initialized to a default value of 0 as instructed. This is used to determine whether or not the log's message is ignored based on the current log level. Now for my first get proc log level system call, I simply return the global process log level. I also used syscall define 0 because there are no additional parameters. For the set proc log level, I first check for sudo by using the capable function, which is a Linux kernel function that checks if the current process has a given capability. The capability I check for is capsysadmin, which provides a broad set of admin capabilities. Capsysadmin is a capability which sudo grants, so checking it will determine if a process runs with these privileges. If not, I return negative eperm, which is the negative error code for insufficient permission. Then I check if the new level is between 0 and 7. If not, I return negative einval, which is the negative error code for the invalid argument. I then set the process log level to the new level, and then I return it. For the proc log message system, I created a character array of size 129 for the 128 characters plus null, and then I created buffers for the executable name of length task length, which is the max length for the process name, and an integer for the PID. First, I do a level check like before, then I use the access OK command in order to verify if the user message pointer is valid before using copy from user. From my research, there are different methods of using access OK based on the kernel version, one which requires a parameter of verify read. So I just use both methods just to be safe. And then I return negative efault for an invalid address or pointer if the access OK fails. Now I can safely use the copy from user function or to copy message from user space to my kernel message buffer. Next, I place a 0 at the end of this buffer, check if the level is less than or equal to the process log level. Next, I use the task PID and R function to retrieve the process ID of a given task structure, in this case, the current task. Get the task name using the getTaskCom function to copy the current process's name into the buffer exe name. I then use snfprint in order to format the characters into the format message buffer with this format here. I used a switch case statement to print the message to the kernel log with the appropriate log level macro. Lastly, I return the level. Now I will unzip my process log tar, cd into process log. Now I'm going to make. Now nano into process log.h. So in this file, I define my process log call number as 337. I define the log names based on numerical levels. I define the headers for my static library functions. And I define my harness functions here. And I will nano into process log.c. Here I define my get and set log level system calls. First function calls the system call get proc log level into a long variable called res. Then it checks if res is negative. If it is, it returns -1 for error. If not, then it returns the result. Same for set proc log level. I call the system call with the input parameter new level. I check if it's negative and I return -1 for error. If not, I return the result, which is the new level. For the process log message, I take the level and the message. I call system call with those parameters with them switched. I check if it's negative again, and I return result. Now for the harness functions. For the retrieve set level parameters, I create an array buffer in memory with 3 values. They simply test malloc to see if it fails. Then I set the elements of the array to the appropriate values. And lastly, I return the array. For the retrieve get parameters, I do the same thing except I create a buffer with 2 map values instead. I set the 0 position, get proc log level, and then number parameter 0. Then I return the array. Now for the interpret set, get, and log message, I check if the return value of the function is negative. If it is, I return -1 to indicate an error. If not, I return the return value, which is the log level. Now we'll compile library test, and now harness test. I will run the library test. As you can see, should fail, fails. Should succeed, changes it to 3. Should succeed, prints the message. Did it print? Yes. Should not print, did the message print? No. Should fail, did the message print? No, and return -1. return -1, and it did not crash. Now we'll run the harness test. Should fail, return -1, did not change the log level. Should succeed, change the log level from 4 to 3. Should succeed, printed the message print yes. And should fail, return -1. And again, I did not crash. I also made sure to apply P1 diff to a fresh kernel in order to make sure that this all functioned.